Assalamu alaikum and good evening, everyone. My name is Sohaib. As Gibran said, I work at Rigetti Computing, where I'm a physicist as well as a software developer. Um, at Rigetti, I work mostly on applications, so that means taking near-term algorithms and implementing them on Rigetti hardware in sort of an optimized fashion, as well as keeping an eye out for any kind of near-term applications applicable for noisy devices that we have in the near term. My background is in physics. I did my PhD in theoretical energy physics from Steve Weinberg's group at UT Austin. I worked at a machine learning startup after that in San Francisco, and subsequently I joined the quantum computing industry at Rigetti. I'm originally from Pakistan, which is why I'm especially excited to see something like this happening in Karachi, and hopefully this is one of several many to come. So I'm going to switch over to my slides now, and I would love if people would just, stop at any point for questions. I'd like to make this as interactive as possible, okay? And I wanted to have a second portion to this presentation, which was going to be sharing of code demonstrations. I think the best way to do that now is to basically, I'll probably just send over some code notebooks to Gibran, and maybe he can share them amongst the participants later. So watch out for those as well. But I'll set the preamble for those, hopefully during the course of my presentation. Okay, so I'm going to see if I can now share my slides. So can you guys see the slide that says Quantum Information Summer School 2019? What, did I hear a yes?
Yeah.
Okay, perfect. All right, and now can you see them in full screen? Okay, perfect. Okay, so let me just first off, start off by saying what Rigetti is. Rigetti is, we're a full stack quantum computing company. We're actually the world's very first. And what that means is that, we deal not just with the hardware side of things. So we not just, build our own chips and quantum devices, but we also build the software layers on top of that. So that involves not just the QPUs, but also the software for the control system. We have a cloud platform living on top of the QPUs, and the way that users actually use the cloud platform itself is via this Python library called PyQuil. And on top of that, people build applications for near-term quantum devices. And most of my work actually happens in the PyQuil and the apps arena. So sometimes I'll be contributing to PyQuil development, and sometimes I'll be actually actively working on the applications. So the question begs itself, why build a quantum computer at all? And the answer ultimately is because classical computers themselves have fundamental limits, right? There are sort of economic limits to how small you can push down classical chips to, right? So you can only go as far as sort of atom size chips ultimately, and at that point you're sort of dealing with you either have to come up with clever ways to deal with problems that quantum mechanics gives you, or you have to find a way to exploit quantum mechanics in some way. And quantum computers take the latter view. They take the latter strategy, and instead of overcoming quantum mechanics, they try to exploit quantum mechanics in some way. You also have diminishing returns to parallelization, such as given by Amdahl's law, which basically says that you can only techniques such as parallelization can help you scale up your classical computing, but that's only to a certain limit and a certain scale. And of course, you have the problem of energy consumption. So the more supercomputers these days sometimes require their own mini power plant to power them through the computations that they need to do. And so the computational demands of the 21st century really demand a new sort of computational paradigm, and we believe that quantum computing is precisely that paradigm. And so one other sort of sell or pitch, elevator pitch that people often give for quantum computers is that the power roughly scales exponentially with the number of qubits. So that means that n bits can exactly simulate log to the n qubits, or in other words, n qubits can exactly simulate 2 to the n bits. And so sometimes, this comparison is given, like the Commodore 64 could exactly simulate 10 qubits. The AWS M4 instance can exactly simulate up to 30 qubits, and the entire global cloud right now can exactly simulate up to 60 qubits. Okay, so that, basically, with every sort of like doubling of qubits, you're getting sort of like 2 to the n more bits essentially. And one other sort of nice mental model to have for quantum computers is the so-called big memory small pipe mental model. So what that means is, essentially quantum computing you can think of as very large, as essentially a very large linear algebra machine. So you have you could have like a very small number of inputs, so n bits or so. But the things that you can do with those n bits, you could basically perform a very large 2 to the n by 2 to the n complex matrix multiplication in a very short amount of time. And that's really the power that quantum computing gives us, like the ability to perform very large multiplications very quickly on a polynomial number of bits. And we believe that quantum advantage is around the corner. Quantum advantage we refer to as the problem, using quantum computers to solve a problem better, faster, or cheaper than is otherwise possible. And we believe that's basically within our reach. I would say maybe if not exactly right now, it should be within our reach in a matter of a few years. And for those of you who don't know, the Rigetti is also, in fact, it has a reward of $1 million for anyone who proves or demonstrates quantum advantage on our Rigetti Quantum Cloud Services platform. So all of you, feel free to compete. Okay, so I'm gonna spend the rest of my talk spending a little bit about the basics of what quantum computing is. I'll talk a little bit about some basic quantum algorithms, and a little bit about some near-term quantum algorithms, and then I'll hopefully after that, you guys can take it on your own with the coding notebooks. But the most basic concept in quantum computing is the concept of the qubit. So the qubit is defined as a superposition of 0 and 1. So the classical bits 0 and 1 combined together in a qubit as basically just this particular linear combination. Alpha and beta can both be complex numbers, and in general are. The only constraint they have is that their modulus squared must sum to 1. And a similar, an alternative but equivalent way to view qubits is through this language of ket. So a 0 classical bit can be viewed as the 1 0 ket. A 1 classical bit can be viewed as a 0 1 ket. And then a general qubit psi is basically just a combination of those two vectors with complex coefficients. So it's in general this vector alpha beta. And the idea behind the qubit is that it's a probabilistic state. So in other words, even though the qubit itself could be in this state, once you observe it or you measure it, you will only measure it with, either in the state 0 or in the state 1. And those measurement comes with certain probabilities. So you'll measure this in the state 0 with probability mod alpha squared, and you'll measure it in the state 1 with probability mod beta squared. Corresponding to the notion of kets is also this notion of a dual space known as the bra space. And this is basically, for every ket, there's a row vector. For every column vector ket, there's a row vector bra, which basically takes the same vector, transposes it, and complex conjugates it. So that basically means if alpha is some complex number, alpha bar is its complex conjugate, and you just take the row vector form of that particular bra, that particular ket or column vector. And in terms of these kets and bras, you can define an inner product. So this, the inner product for some general phi and psi is defined as follows. So psi is, again, just alpha and beta, and phi is now gamma and delta. And in terms of these, you can basically define an inner product. And why is the inner product important? Well, for one thing, it leads to our normalization requirements. So all quantum states are required to be normalized. And essentially that basically, translates to the same condition as alpha mod squared plus beta mod squared summing to 1. And we previously said how alpha mod squared and beta mod squared were respectively the probabilities of measuring that quantum state psi in the 0 or the 1 state. So therefore, this is basically, the normalization condition is basically just saying that probabilities have to sum to 1. Okay? That's really all that it's imposing. And so, again, equipped with the notion of an inner product, we can also reinterpret these measurement probabilities as basically the inner product of the 0 state with psi. So that gives you the coefficient of, of the 0 state in psi. And the coefficient of beta mod squared is also given by the inner product of the 1 state with psi, modulus squared. Okay? And the qubit state, a single qubit state, can also be very conveniently parametrized and visualized as points on a sphere. And the sphere is known as the Bloch sphere. And the parameterization goes as follows. So it's basically cosine of some angle divided by 2 plus e to the I phi times sine of the same angle divided by 2. This theta angle is basically, you could think of this as the angle that the state makes with the z-axis. And the phi is the angle that you can imagine that as basically the projected psi onto the xy plane and the angle that that projection makes with the x-axis. Notice that, this is kind of a funny sphere in which the 0 state lies at the North Pole and the 1 state lies on the South Pole. And 0 and 1 are, strictly speaking, they're orthogonal to each other in the sense of the inner product. So if you calculate the inner product of 0 and 1, it'll come out to be 0. However, seen on this sphere, they look like they actually lie along the same axis. So it can be a little non-intuitive, but it's a very convenient way to parameterize essentially all single qubit states. So in other words, there's a one-to-one correspondence with all possible single qubit states and points on this, two-dimensional sphere. Okay, so we said quite a few things about single qubit states. What about multiple qubits? Well, so there's one straightforward way in which we could, create multiple qubits out of just single qubits is essentially just to tensor product them together. So a tensor product is defined as this particular beast. I've written it out just for sort of like clarification. An explicit example in the case of, tensor producting 2 qubit states. But essentially, you could think of that as just like, it's generalizing the notion of some like product space, essentially. And there's a very calculable way in which to do this. So for example, if psi is this particular, ket or column vector and phi is this particular column or ket vector, you can think of like, basically alpha naught multiplying that particular phi and alpha 1 multiplying that particular phi. Those together combine to form a higher dimensional, vector. And that's basically, and this product is associative, so that means that psi, product phi, products, gamma, like they satisfy these kind of like nice relationships. It's not commutative, so in other words, psi, product phi is not the same as phi, product psi, which is important. Okay, so that's how you can build, multiple qubits out of single qubits. What about operations? So the most general way in which you can evolve the state of a qubit is through the use of unitary operators. And in quantum computing, unitary operators also go by the name of gates. A unitary operator is basically just a complex matrix whose inverse is given by its transpose conjugate. So if you complex conjugate every element of that matrix, and you take its transpose, you multiply those two things together, you'll get the identity. And the reason why these are the most general possible operations that you can apply on a pure qubit state is because they're the most general things that preserve norm. So like, well, I shouldn't say maybe the most general, but like one property that they do satisfy is that they satisfy the inner product. So in other words, if two particular kets have some particular inner product, under a unitary operation, that inner product will remain preserved. And in particular, remember that the norm is also a kind of an inner product. It's just an inner product of a statement itself, right? So in other words, the unitary operation will essentially preserve norms as well. And that's something that we require for any kind of consistent quantum mechanics, right? Because probabilities always have to sum to one, right? Okay, so now we've talked a little bit about qubits and what their what multiple qubits look like and what their operations look like. It would also help at this point to sort of like create some sort of like a table to distinguish between bits and probabilistic bits, which is basically the closest classical cousin to qubits as well as qubits. So classically, like in classical computers, everything works in zeros and ones in binary language, right? So we have like zeros and ones, and states could be like a single bit character can exist either in the state 0 or it can exist in the state 1. However, we could generalize that notion to the notion of a probabilistic bit. We could say that like we have some vector b that is a linear combination of 0 and 1, such that the coefficients a and b specify the probability of measuring this particular bit in the state 0 or in the state 1. And because they're probabilities, they both have to sum to 1, okay? So it's a very small, so this is a purely classical thing. There's nothing quantum mechanical about this. This is something that you can build with a classical computer, okay? Where quantum mechanics comes in, and this is basically what I was saying, like, the coefficients specify respectively the probabilities of 0 and 1. Quantum mechanically, it's a small but significant leap to go from a probabilistic bit to a qubit. You say essentially that like these coefficients that previously specified the probabilities of measuring either 0 and 1 now just become complex coefficients. Okay, so they're no longer just real numbers. Now they're in general complex numbers, and we could still sort of like recover a probabilistic interpretation out of these coefficients by saying that the modulus squared of those things are now the probabilities respectively of observing 0 and 1. And because these things are probabilities, we require that they sum to 1. Okay, so notice that it's a very small but subtle but important shift in going from classical to quantum, right? So we just said like we literally just replaced the coefficients from being real to complex. Okay, so classically, in the case of like probabilistic bit, if we were to think of a coin, we would, or I should say a fair coin. We could describe this by the probabilistic bit 1/2 0 plus 1/2 1, right? So that basically just means that like, and you could sort of like assign the 0 state to the head state and the 1 state to the tail state, and you're saying that if you flip a coin, 1/2 of the times roughly you'll find it to be in the head state or the 0 state, and the other remaining half you'll find it to be in the 1 or the tail state. A quantum coin, on the other hand, could be any one of these several states. So it could be precisely the corresponding quantum version of this classical coin, where you basically just take the square root of those coefficients, or you could also add a relative phase between those two. So over here we've added e to the I pi. Over here we've added I times e to the I pi, etc. And in general, basically, you could have like 1 over square root of 2 plus any phase difference that you want, between 0 and 1 divided by the square root of 2. And if you take the modulus squared of these things, you'll find that this is basically mod squared of 1 over square root of 2. Of course, is just 1/2. The mods squared of this one particular thing is again just 1/2. So this is consistent, right? So this again just gives us like 1/2 probabilities for measuring 0 and 1 respectively, and that's a whole family. This is an infinite set of quantum states essentially that can specify a so-called fair coin state. Okay, and these things are precisely the things that lie on the equator of the Bloch sphere. So the 0 is at the North Pole, the 1 is on the South Pole. And exactly in the middle or in the equator are basically all these quantum coin states. Okay. So now, we could generalize, from going from a single probabilistic bit, we could go to multiple probabilistic bits, right? So like we can imagine a classical bit string, right? So like instead of like a single bit character carrying either 0 and 1, we could imagine, like say like a 3-bit string, which could be 000 or 011 or any of the 8 possible combinations of zeros and ones for 3-bit characters, right? And similarly, we could imagine a probability distribution over those bit strings, and that becomes our probabilistic bit vector, where basically, essentially, every coefficient essentially just gives you the probability of measuring that particular bit string, and those coefficients, now interpreted as probability amplitudes, they have to sum to 1 in the case of probabilistic bits. In the case of quantum bits or qubits, you essentially have the same thing. You're just tensor producting, those states, individual states together, and you're saying that like, the coefficients now have to modulus squared sum to 1. In the case of probabilistic bits, we also have, the most general way in which we could evolve a probabilistic bit is through the use of stochastic matrices. So these are matrices whose, depending on, how you define them, in this particular case, you're basically saying that like their rows have to sum to 1. And that just basically means that a probabilistic bit has to have all of its elements summing to 1. And so a stochastic matrix should, transform a probabilistic bit to another probabilistic bit, which would again, have all of its elements sum to 1. A qubit, like we argued earlier, can be evolved more generally through the use of unitary matrices and not just stochastic matrices. And so notice that it's these really small but subtle differences between probabilistic bits and qubits, namely that we have complex coefficients instead of real coefficients, we have unitary matrices instead of stochastic matrices. It's these small but very important differences that we believe give quantum computing their entire computational power. It's because of these differences that essentially quantum computers would be able to do things that classical computers never would be able to. So it's important to note what these differences are. Okay. So now, we talked about that, the fact that, we have unitary matrices and stochastic matrices for qubits and probabilistic bits, respectively. We could also, once we apply an operator to probabilistic bits, we can, we get some particular, final state, and we can sample from it, and we can, in order to get individual bit strings, right? And we can do the same thing with qubits. So essentially, the Born rule tells us the probability of sampling a particular probabilistic bit, of sampling a particular bit string. And so via the Born rule, we can sort of go from qubits to probabilistic bits simply by saying whatever the coefficients are for a qubit, that coefficient modulus squared, if we construct, a vector of those coefficients modulus squared, we'll get precisely the probabilistic bit corresponding to that qubit, which we can then sample to, observe some particular bit string with some particular probability. And that's the act of measurement. Okay. Okay. So we talked about what, unitary operations. Let's start digging into some specifics. So the most basic operations that you'll find in, quantum computing are these so-called polygates. Namely the identity, the X gate, or the NOT gate, the Y gate, and the Z gate, and they're defined in matrix form as follows. Let's take a quick look at what their operation actually does. So the identity gate, as the name implies, it basically leaves the qubit alone, right? So I acting on 0 just leaves it in the 0 state. I acting on 1 leaves it in the 1 state. And in matrix form, you can see this quite explicitly as follows. I think I might have mixed up these vectors over here. This is supposed to be the 1 state, and this is supposed to be the 0 state. But it doesn't really matter. The X gate is the so-called NOT gate, or the flip gate, which, as the name implies, it basically just flips, the 0 state to the 1 state, and it flips the 1 state to the 0 state. And then again, you can see this quite explicitly in matrix form if you actually compute the matrix vector multiplication. The Y gate is sort of similar to the X gate, except that it adds a phase. So in the case of 0, it adds a phase of I to the resultant state 1. When it acts on the one state, it adds a phase of minus I to the resulting state 0. The Z gate finally is, it leaves, it's sort of like the identity, except that it also adds a phase. So when acting on the 0 state, it leaves it alone, it acts as the identity. When it acts in the 1 state, it adds a phase of -1, okay, like over here. And finally, another important gate that's often used in quantum computation is the Hadamard gate, defined in matrix form as follows. And the important thing to note about the Hadamard gate is that it produces an equal superposition state. So if you start off from the 0 state and you apply the Hadamard gate, you'll end up with a state that's sort of like the quantum coin that we just described earlier, except that it has a phase of 0. So it has, like the resultant state is also often called the plus state, and you'll find it to be, like if you measure it, you'll find it with equal probability to be in the 0 or the 1 state. Similarly, you can apply the Hadamard gate on the 1 state, and you'll get another quantum coin, except now this quantum coin exists on the exactly opposite point on the equator as the plus state, and this is called the minus state. In fact, on the Bloch sphere, if you were to visualize this plus state lies exactly along the x-axis, whereas this minus state lies along the negative x-axis. Okay, but the probability statistics for both of these states are the same. So if you measure them, you'll find that with equal probability, they'll come out to be in either the 0 or the 1 state. Okay. And examples of quantum operations on multiple qubits, again, we basically would just tensor product together, certain operations. So, for example, over here, I'm applying the identity to this particular qubit, the X gate to that particular qubit, resulting in the 0. So this qubit just becomes 0, that qubit just becomes a 1, and I can write this equivalently in sort of much more compact notation by just adding subscripts over here. So in our notation, the rightmost qubit is the 0th qubit, and every qubit after that is like it increases its index. So for example, this is the 0th qubit, this is the first qubit. If there was a qubit over here, that would have been the second, and so forth. So this is just saying apply the identity on the first qubit, so leave it alone. This is saying apply the X gate on the 0th qubit, so flip it, and resulting in the 0-1 state. Similarly, over here, we're applying the X gate to the first qubit and the Hadamard gate to the 0th qubit, resulting in this particular state. So the 1 tensor producted with the plus state, which if you carry the exercise out, basically this is just saying like it's the 1, 0 plus 1, 1 state. And I just saw a typo there. There should be a square root over here. Okay. So just as we defined a tensor product for qubit states, there's also a tensor product for qubit operations. So like in the previous slide, we had multi-qubit operations, and so those multi-qubit operations, if you were to express in matrix form, you would basically just compute their tensor product like so. And the idea basically goes the same way. Like you just basically take if you were tensor producting A and B together. You basically just think of this as like, every element of A multiplying the entire matrix B. So A naught naught multiplies this entire matrix B, A01 multiplies that entire matrix B, and so you have like a mini matrix over here, etc. Okay, so there's another view of quantum operations and qubits, and this is actually the one that you'll find the most, ubiquitous in quantum computing, and that's the view of quantum circuits. So in a circuit diagram, essentially, you're just like sort of like applying, you're sort of making a bit more intuitive what you're actually doing with individual qubits. So the simplest example, or one of the simplest examples you can think of is like, to the qubit state 0, apply the X gate. This is basically just like, you start off with some 0 state. There's a wire coming out of that qubit, and then you apply the X gate, and the wire coming out of that qubit, or after that operation, is going to be the 1 state. Similarly, if you apply like X to the first qubit, H to the 0th qubit, you can express that in circuit diagram as follows. And finally, after you run the circuit diagram, you can also measure out the qubit state and find it to be in the 1 state or the 0, 0 state, respectively. And that's what this arrow with, this kind of squiggly arrow thing denotes. It just denotes a measurement process. And finally, there's the fourth, and for our purposes, probably is like the most important view, which is of writing quantum operations, which is in the form of quantum programs. So this is a snippet of using the PyQuil library that I mentioned earlier. This is the library that Rigetti hosts and uses. This is the library that you would use if you were to actually program our particular quantum computers. So what we're doing over here is we're basically specifying a program that applies the X operation on the 0th qubit. We're also instantiating a quantum computer device. We're saying, just get me like a 9-qubit generic QVM. So the QVM stands for quantum virtual machine. What it is essentially just a classical computer masquerading as a quantum computer. So oftentimes, before we actually run programs in the quantum computer, we would also like to run them, sort of like as a sanity check on a classical simulator. So this is a classical computer simulating a quantum device. And we do this just as sort of like a sanity check and just to see that our program is actually giving what it's supposed to be giving before we actually run it on, using expensive QPU time and, against a noisy device, which may not often give us like the most ideal results, right? So over here, we're applying a very simple program. We're applying the X gate to the 0th qubit. We're taking a 9-qubit quantum device, and we're saying basically just like run and measure that program, and run it for a total times of 10 trials. Okay, so remember that quantum devices are probabilistic devices. So oftentimes, we'll only get in order to learn what the underlying quantum state was, or what the probability distribution was, we have to run it for more than just several, more than just a single shot. Although in some cases a single shot could suffice, but in practice, definitely want to specify several trials or several, samples from the resultant state. So if we print this, if we run this particular program and we obtain the results, because this is a simple enough program, the X gate always results in the 1 state. So no matter how many trials we specify, we'll always just get the 1 state out of that, right? And so this is all that this specifies. We can write this, the same thing, in a somewhat more complicated manner. And this is sort of like, giving you a peek about what actually happens a little bit more under the hood in PyQuil. So what happens is, we're declaring a program, and we declare, along with that program, a readout register. That's what the RO stands for. And we're saying that it's going to carry 1 bit of classical information. Okay. We then instantiate the X gates. In other words, we apply the X gate on qubit 0, and then we say we're going to measure out qubit 0 and store it in that single bit classical register. And then we're going to say we're going to repeat that entire process a total number of 10 times. Okay. And this particular step basically says, we have a quantum computer, or we have some quantum resource, and we're going to compile our program into an executable for that quantum resource. Okay. And then finally, we're going to run that executable, and then we'll print the results. And lo and behold, we're going to see that it's just basically a series of ones, because it's a very, very simple program which results in a deterministic state. The state being 1. And just to sort of give you a peek under the hood of further peek under the hood. So PyQuil is actually a Python wrapper for the Quill programming language, and Quill itself stands for Quantum Instruction Language. I'll have a bit more to say about Quill itself, but right now, essentially, just keep in mind that if you sort of print out this particular program, you'll see the following printout statements, and this is basically the actual Quill program that you're carrying out. So this is basically, saying the same thing that we'd said before. You declare some classical readout register, you apply some quantum operation on some specific qubit, And then you measure out that specific qubit, and measure out and read out and store the measurement result in some classical register. That's readout register 0. Okay, so that's the quill program that's actually being carried out by this particular Python snippet. Any questions so far? Okay, I'm going to take that as a no. All right, so carrying on. Here's an example of a more complicated quantum program. Slightly more complicated. Like in this case, it just involves 2 qubits. We have, the X gate being applied to qubit 1, the Hadamard gate being applied to qubit 0. And in circuit form, we already saw that it looks like this. In quantum program form, we can essentially repeat the same exercise we did before. We just now declare a 2 classical bit register. And we apply the Hadamard gate and the X gate. We measure out both the 0s and the 1 qubits, and we store the results in these classical registers. And we carry this exercise out for a total of 10 times. Because the first operation is deterministic, we'll see that that this particular qubit or this particular readout register has only ones over in its readout register, right? Whereas the Hadamard gate produced an equal superposition state. So roughly 50% of the times in this index you'll see 0s, and the other 50% of the times you'll see 1s. And that's exactly what you get over here. And of course, you could come up with more and more complicated programs. You could think about sequences of the operations like X followed by Y on qubit 1, Hadamard followed by Z on qubit 0, etc. It's just a matter of concatenating these various gate instructions, followed by sandwiched between a declaration of classical register and some measurement commands. Okay, so here's where I would have if I were actually physically present there, I would have stopped there to perform a simple kind of coding exercise. But this would have to wait for, you guys can maybe play around with it on your own time, maybe set some, later point in time. But one of the simplest exercises you can do when you start to, program quantum computers is to create an n-sided dice using a quantum computer. So what that means is that, if you talked about a quantum coin, for example, right? That's an example of a 2-sided dice. And an n-sided dice would just be something that would give you any one of n states with equal probability. Okay, so the first question is, what gate would we use? And the answer to that is, we already saw that we were going to talk about we talked about the Hadamard state as essentially producing an equal superposition state, and so that's the gate that we would use for n qubits. And the next question is, how many qubits would we use? Well, so 2 to the n qubits specify 2 to the n states. So in other words, if we need an n-sided dice, we can solve for 2 to the n equals n, and that basically gives us log n to the base 2, essentially. So in other words, if you wanted to produce an 8-sided dice, you would need 3 qubits, essentially. Okay. So one other concept that is pretty core to quantum computation is the idea of projections. So projection, as the name implies, is basically just projecting a vector or a ken or a bra along a given ken or a bra via its corresponding projection operator. So for some quantum state psi, the corresponding projection operator is given by the outer product, which is defined as follows. And examples of this is, for example, a projection operator along the 0 state. So what this means is that essentially you're given some generic qubit state psi, and you're saying okay, I want to basically just project it along just this particular state that I desire, right? So the P0 projection operator in matrix form is 1 0 0 0. P1 projection operator is given as follows. The P plus projection operator, which is basically the equal superposition state, that's given as follows. And most generally, you can define it via its outer product. So for any given psi, this projection operator applied to some other qubit psi will basically result in a vector that's parallel along, that's pointing along the direction of psi. Okay. And in matrix form, the most general form that you can write is as follows. And the reason why projections are important is because in terms of those, you can define a very important class of quantum operations called controlled operations. So controlled operations you can think of as sort of like the quantum versions of if-else if statements, right? So if the qubit state is in, so over here, remember that, the qubit 0 is the rightmost qubit, qubit 1 is the qubit to the left of that, etc. So if qubit 1 is at the state 0, apply the identity to qubit 0. Else, if qubit 1 is in the state 1, apply the operation U to qubit 0. This is what this particular controlled operation is saying. Okay? And for example, like the most famous example of a controlled operation is the so-called C-NOT gate, or a controlled NOT operation. Remember, the NOT operation was specified by the X gate. So all we're saying is basically, if this particular qubit is in the state 0, apply the identity. And if it's in the state 1, then apply the NOT operation. And in matrix form, it looks like this. And this is something, again, that you can calculate for yourself using the tensor product that I defined earlier, and then just summing up those two matrices. Okay. Entangled states. So the reason why the controlled operations are so important is because they produced an important class of quantum states called entangled states, which are, an important reason why quantum computers are thought to be, are thought to have or believed to be, have some sort of computational speedups over classical resources. An entangled state is defined as a state that cannot be written as a product state. So, that's basically just the definition, the most general definition. As an example of a state that is non-entangled is, for example, this particular state. So 1 over square root 2, 0, 0 plus 0, 1. And the reason why that's not entangled is because I can write this out as a tensor product state that looks like follows. So I can write it out as 0 tensor product 1 over square root 2, 0 plus 1. Or in other words, 0 tensor product the plus state. An example of a state that is entangled is the following. So 1 over square root of 2, 0, 0 plus 1, 1. No matter how hard you try, you cannot decompose this and write it into this particular, in a form that's basically says some qubit state, some single qubit state, tensor product with some other single qubit state. You're never going to be able to write a state like that in that form. And that's the reason why we say it's entangled. And the word entangled is supposed to sort of refer to the fact that, the state of this particular qubit, qubit 1, affects the state it's entangled with the state of qubit 0. Okay, you can't disentangle them and write them as a product state at all. And so here's a very simple circuit that produces one of the simplest entangled states, which we call the Bell state. And the way we do that is to basically apply the Hadamard gate on qubit 1, and then followed by a C-NOT operation with the control qubit being qubit 1 and the target qubit being qubit 0. And here we'll actually use the wave function simulator provided by Pikewell. The wave function simulator is essentially, again, it's a classical simulator that helps you sort of visualize what the quantum state actually is. Now, of course, you won't be able to do this for too large a number of qubits, but what it again does, let you do is basically just sort of troubleshoot through your code and allow you to see that what you're doing actually makes sense. On an actual physical quantum computer, of course, you'll never actually have access to the quantum state itself. You will only be able to make measurements to make sense of what the quantum state would be, post measurement, essentially. But yeah, so you can define this very simple program, a Hadamard followed by a C-NOT, and you get this Hadamard state, 0, 0 plus 1, 1 divided by square root of 2. Sorry, you get the Bell state, not the Hadamard state. And one other thing that projection operators allow you to do is the ability to measure in some arbitrary basis. So the standard basis that we measure things in is so-called computational basis, right? So this is the 0 and the 1 state. If you were to measure, any particular state psi, you can sort of think of that as an expectation value. So what that means is, you sandwich the projection operator between those two states psi. This is the same thing as basically the inner product of psi with the state 0 modulus squared. And so this is sort of like, another way to think about what those probabilities actually mean. But it also, written in this way, it sort of like lends itself to a nice generalization. So you can say that, like, okay, imagine some other basis. So instead of the zeros and the ones, we sort of like rotated or shifted or transformed our basis into some other basis that's related to the earlier basis through this change of through this unitary transformation, right? So now we have the basis vector 0 prime and 1 prime. And in this particular basis now, we can apply, we similarly have that we'll get 0 prime with probability, given by the expectation value of this projection operator, and we'll get 1 with the expectation value of this particular projection operator. And essentially, all that means is that measurement of psi in some shifted basis it just means that, like, if you know what that transformation matrix is, you just take the transpose conjugate of that matrix and you tack that on to the very end of your program, and then you measure in the standard computational basis. Essentially, that's really all it means. Okay, so equipped with all these notions, we can actually carry out like one of our first quantum algorithms. Historically, also one of the more famous ones, and goes by the name of quantum teleportation. And as the name implies, the goal of this protocol or this algorithm is to teleport a qubit. Okay, so imagine the following scenario. We have Alice and Bob. Alice is in possession of some qubit psi, which she would like to teleport over to Bob, who is at some distant location. Okay, and the protocol for quantum teleportation is as follows. We create a Bell state, the entangled state that we just described, and we give one qubit of each of those entangled pairs, one to Alice and the other to Bob. We have Alice measure both her qubits in the Bell basis, and we just saw how we could measure things in any arbitrary basis. So Alice is going to measure both her qubits in the Bell basis, and then she's going to send her results over to Bob. Bob will then conditionally apply gates to his qubits based off Alice's measurements in order to reconstruct the original qubit at his particular location. Okay, so in circuit diagram, it kind of looks as follows. So here's the Bell state that we prepared. Here's Alice, and here's Bob. Okay, so Alice wants to teleport this particular qubit psi over to where Bob is. And, Alice and Bob could be light years apart. Okay, like the only thing that's teleportation requires is that they share an entangled source. Okay, so initially we must entangle this pair, and we must distribute one qubit, to Alice and the other qubit to Bob. Alice is then going to measure her pair of qubits in the Bell basis, and this is going to result in two numbers, A and B, and both of A and B are going to be either 0 or 1, right? And so depending on the values of A and B, Bob is going to apply this sequence of gates X and Z, conditioned on these particular values. And in so doing, Bob is then able to completely reconstruct the quantum state psi. And so in effect, what we've done is, we've destroyed the qubit state that Alice originally had over here because we measured it out. And we reconstructed it where Bob was. So in effect, we've sort of teleported that qubit psi from wherever Alice was to wherever Bob is. So here's kind of what it looks like a bit more explicitly in circuit form. So we prepared the Bell state, right, which was, as we saw before, is prepared by a Hadamard gate followed by C0 gate. And we give one pair to Alice, and the other is, kept with Bob. And Alice, wants to teleport this particular qubit, the ancilla Q. And she measures both of her qubits in the Bell basis. So remember that, we said that, like, okay, if you were to, if some basis is related to the computational basis through U, through some unitary transformation U, then all you have to do is just basically attach like U dagger at the very end. And that's essentially all we're doing. So, U in this particular case is given by H followed by C0. And so the dagger of that is just a C0 followed by an H. So you do that, you measure those things, and then we're saying, like, depending on the values of those two measurement values, we'll either apply the X gate or the Z gate, or we won't. And for those of you familiar with assembly language, this is very similar to the case of like, when it's when certain like low level, like assembler level languages, like, we like to produce labels and jump or branching commands. And exactly the same sort of thing that's happening at the level of Quill. So the code that you're seeing over here is the quantum instruction language. This is the Quill programming language, and it essentially allows you to do this kind of like branching off of quantum circuits depending on classical measurements. Okay, and in PyQuil, like all of this gets, of course, wrapped up into like nicer and easier to write language. You can, basically say like, okay, like, apply some operation and store that operation, like measure out that qubit 0 and store that result in some classical register. Depending on the value of the classical register, either apply some program or apply some other program. So this is basically saying like, apply the X gate to qubit 0, measure out the qubit 0 and store its value in this particular readout register. If this readout register says 1, this is what this is saying, then apply the X operator onto qubit 1. And if the readout register says 0, then just apply the identity. Okay, so if we apply the wave function simulator on this, we'll find that it basically just creates the 1-1 state. And similarly, like we can think of like a similar program where we apply the identity gates and similarly apply an if then else kind of like logic. We say like, okay, if this is 0, then similarly apply the identity. If this is 1, then apply the X gate. But because the identity just results in a 0, over here we should just see the 0-0 state. Okay. Okay. So the next algorithm that I want to talk about is Deutsch's algorithm, and this is historically one of the first algorithms that talked about the so-called like quantum advantage, or like that illustrated in a sort of like more or less concrete form how quantum computers could be able to give us a computational advantage over classical computers. And it's described in the form of an oracle or a black box function. So by an oracle, I basically just mean, imagine that, somebody just gives you, as the name implies, like a black box, right? So like, I mean, they say like, okay, here's some function, I don't know, it could be any function, like a function that takes the square root of numbers, or a function that, takes n to the power of like 10 to the power of like, the input or what have you. You could like hook up any function you want. But we have a black box for this function. What that means is that, I give it an input and it gives me an output in order one time. Excuse me. So the idea being that like, I can make a single call to this black box, and this black box will return the value of some particular function. Okay. So Deutsch's algorithm asks the following question. So let's suppose that we have some binary function f that takes values in 0 and 1, and also takes values over 0 and 1. And our goal is to determine whether it is constant, and by that what we mean is that f of 0 equals f of 1, or it is balanced. That is to say, f of 0 is not equal to f of 1. Okay, so, and in the case of constant, of course, f of 0 could be f of 0 and f of 1 could both be 0, or they could both be 1. And in the case of balance, it could be the case of f of 0 is 0 or f of 0 is 1. But, whatever value f of 0 takes, f of 1 has to be the opposite value. Now, classically, of course, we would need exactly 2 steps, right? We would first calculate what f of 0 is, record that number, and then we would calculate what f of 1 is, and then we would record that number, then we would compare those 2 numbers, and then see if those agree. If they agree, then it's a constant function, and if they're balanced, if they don't agree, then it's a balanced function. Okay, but the point being that classically, we would need to make 2 calls to the black box function. In quantum computing, it turns out that via Deutsch's algorithm, really only need to make a single call to the oracle function. And so let's see how. So the unitary equivalent of the black box function is defined as follows, right? So if you have two qubits, x and y, and you have this black box oracle, u sub f, and u is deliberate because this is saying this is a unitary operation, then it results in the state x product y plus f of x, where this plus is now plus, mod 2. So in other words, this is like binary addition. So 1 plus 1, for example, is going to equal 0. But 0 plus 1 or 1 plus 0 is going to equal 1, and 0 plus 0 is going to equal 0. Okay, so this is basically what the black box operation does in the case of quantum operators. Okay, and using this, what we can do is cook up a very special state. So it's like we can prepare x to be the plus state, and we can prepare y to be the minus state. And if we do this, we'll find that this black box operation has the following effect. It creates an overall phase that depends on f of 0, and it creates a relative phase between the 0 and 1 states on this particular qubit, depending on both the values of f of 0 and f of 1. Okay? So now here's the trick. If f of 0 equals f of 1, then the black box operation on this particular state results in the plus state being created on qubit 1. And if it's balanced, which is to say if f of 0 is not equal to f of 1, then the black box operation applied on those qubits results in qubit 1 resulting in the minus state. And now remember that, we talked about how if we know, like what sort of, so the plus state and the minus state are again some sort of like computational basis elements, right? And they're related to the standard computational basis elements via the Hadamard operation. So if we apply the Hadamard state to 0, it'll result in the plus state. If we apply the Hadamard to the 1 state, it'll result in the minus state. And so essentially, if we just apply the Hadamard dagger, which is again just a Hadamard operation, if we just apply the Hadamard at the very end and we measure it out, we'll find that if the function is balanced, or sorry, if the function is constant, excuse me, we'll always measure out qubit 1 to be in the 0 state. And if the function is constant, if the function is balanced, then we'll always measure the qubit 1 out to be in the 1 state. And so this basically results in a deterministic algorithm that, really, and notice that we only took like one single call to the oracle. So classically, even though we needed two calls to the oracle, one to determine f of 0 and the other time to determine f of 1, in quantum computing, essentially we're just applying a single black box operation to determine once and for all whether the function is balanced or constant. And so this is kind of a cooked up problem, but it's it's one of the first that sort of like illustrates the idea of like using these principles of like quantum superposition quantum superposition and sort of like parallelism to determine an answer in a much shorter sequence of gates or operations. Okay, so the next kind of like algorithm that also talks about an advantage, historically one of the first, is the so-called Grover's search algorithm. And over here we can sort of like cast it in the form of the following goal. We say that we have some function that takes values over n-bit strings, and it's again a binary function, so it results in either the 0 or the 1 values. We want to find the bit string such that f of x equals 1. So in other words, we're basically just searching through an unordered database, right? So each of the 2 to the n bit strings you can think of as like some sort of like elements in a database, and you're basically tasked to find some particular element within that database. Okay, and we're just saying that like the particular element that you want to find, like f of x is 1 for that, and f of x is 0 for everything else. So again, we return to the quantum black box, and the unitary equivalent of which results in the following way. So x unitary of like the quantum black box for f applied on x tensor product y results in this particular state. The idea behind Grover's algorithm is as follows now. we first prepare the query register as an equal superposition over all states, right? So like now, this capital N is the same as, 2 to the number of qubits, essentially, okay? And X is all possible bit strings. And so notice that we can rewrite the same thing as 1 over square root of n psi good plus the remaining coefficients times psi bad, where psi good is basically, like bit string that we want to find, right? So this is basically the element in the unordered database that we want to find. And psi bad is just like everything else, okay? If we apply the Oracle black box to this particular operation, or to that particular state, using a qubit 0 as an ancillary qubit, we'll find that it becomes 1 when the psi is basically like the psi that we actually want to find, and a result stays in 0 otherwise. Remember that f of x is 1 for this particular bit string, and f of x is 0 for everything else, right? So you just add a 1 to the 0 state when you have psi good, and you just add 0 when you have psi bad. Okay. Now we also define a phase shift operator. So this is defined as follows. We say, in terms of psi, where psi is now the equal superposition state. This is the quantum dice example that we talked about earlier. Okay. It will transform psi to psi, but it will transform every other x, every other bit string, to the minus of that particular bit string. Okay. And so now, in terms of this, we can define this phase shift operator as follows. We say, like, 2 times the projection operator on the equal superposition state minus the identity. And the thing that this does on any particular quantum state is this effect called the so-called inversion about the mean. And you can sort of like visualize it through this equation. You could say, like, so over here we have some generic coefficients. We have a generic quantum state with some generic coefficients. And what that operator does on that particular state is to basically shift every coefficient alpha. And these alpha over here are, by the way, now real. And this alpha, like this basically depicts the average of those alphas. And so this is basically saying, like, 2 times the average minus those coefficients. That's what those coefficients transform to. A little bit more visually, I guess, maybe I would get to that in a second. But essentially then, Grover's algorithm becomes the following way. We say that, like, okay, like, again, just in the case of like Deutsch's algorithm as well, we prepare a special state, in this case the minus state, as the ancillary qubit in order to get this sort of like phase kickback. Okay, so like, I mean, the trick in Deutsch's algorithm, as well as Grover's algorithm, is to prepare some, special states so that, like, when we apply the black box operation, we'll get the value of that function and store it in some phase information, okay? And so the Grover's search algorithm now becomes the following. We prepare some initial state. We prepare the initial state, given by the Hadamard state and, like this minus state. So we have like a whole bunch of pluses, tensor product the minus state. And then we apply the Grover iterates, which is basically the black box operation followed by this phase shift operator several times, a total of order square root of n times. And we'll find that, like, so in effect, basically what it does is it ends up amplifying the amplitude of the good string, the good bit string that we wanted to find. Like in a single operation, it will do this. And if we do this like several times, in a row, it will end up basically amplifying the probability of finding good bit string. And it will reduce the ability of finding the bad bit strings, after a total of square root of n operations. So notice that the square root of n is important, right? Because if you think about it classically, if you were to search over an unordered database, it will take about, like in the worst case, it will take about n shots, right? So if you have like 10 items and they're all in some like, like in a completely unordered mess, and someone was to say like, okay, out of these 10 items, search, some special item X, right? In the worst case scenario, you would have to search through all 10 items to get to item X. In the case of Grover's algorithm, you only need to apply this algorithm a total of square root of n times. And so this is an example of something that gives you a polynomial speed up over the best classical algorithm. Okay, so the previous examples that I gave of like Grover's and Deutsch's algorithm, these are all still sort of like in the context of, I would say like these are kind of like classical textbook style algorithms that people often discuss as sort of like as when you're sort of like first learning about quantum computing, but they're not very relevant for like solving any sort of like practical problems, at least not in the near term. So in the near term, people turn to, often turn to this large class of algorithms called variational algorithms, and the more famous of those is known as the variational quantum eigensolver. The schematically, it sort of like says the following. So the goal is to find the ground state of some Hamiltonian H. H is, so Hamiltonian is a term borrowed from physics. In physics, it really just denotes the sum of the kinetic energy and the potential energy. But Hamiltonian, in the context of quantum computing, is often used to denote like all sorts of things. And most broadly, it's supposed to refer to some objective function. Okay, so you want to minimize some objective function, and you want to find the state that minimizes that particular objective function. That's sort of like fits the bill of several problems, not just like chemistry and physics style problems, but even combinatorial optimization problems. But for the specific case of solving sort of physics problems or chemistry style problems, and this is problems along the lines of like, here's some very complicated molecule. Let's find the ground state of this molecule. Remember that quantum computers initially sort of came about, or they were envisioned or dreamed of precisely because of the fact that nature evolves according to the laws of quantum mechanics, and classical computers cannot directly simulate quantum mechanics, whereas quantum computers can. And so, because of their ability to directly simulate quantum mechanical systems, quantum computers are expected to one day, give us the ability to simulate, nature at its most fundamental scale. Now, of course, something like that requires the era of like error-corrected, fault-tolerant quantum computers. In the meantime, like people have shown that something like this prescription will work pretty well. So the general procedure is you say that like you prepare some trial quantum state, psi, as a function of some parametric quantum circuit, and this is where I think like probably once you get to play around with the code notebooks, things will become a lot clearer by what I mean by a parametric quantum circuit. But essentially, you can think of this as like some circuit that depends on some parameters theta. And so you prepare some trial state psi. You can calculate its expectation value. You can calculate the expectation value of the objective function or the Hamiltonian in that trial state. And then finally, you find the values of theta that will minimize that expectation value. And so the particular values of theta that will minimize this, those give you the particular trial state that is in fact the same as your ground state. And so the minimal expectation value is the ground state energy, and the theta that corresponds to that particular minimal expectation value also gives you the ground state. And so this has helped, chemists find ground states of very large molecules. It has also helped physicists find, ground states and phase diagrams. So, they're beginning to find, apply this to certain, toy systems that, we hope one day extend to, larger systems. But okay, so another specific example of variational algorithm is the so-called quantum approximate optimization algorithm, or the QAOA for short. And the QAOA is designed to solve combinatorial optimization problems. And it's most like sort of like broad in mathematical form. A combinatorial optimization problem is defined as in terms of binary constraints. So imagine that you have some bit strings, right? Some sequence of zeros and ones, and you have some constraints over them. So you say that like, okay, you have some constraints labeled by alpha, and you say that like C of like alpha of that bit string is 1 if Z satisfies the constraint alpha, and is 0 if Z does not. So the goal is now to find a bit string that maximizes the objective function, which is the sum of all those constraints. Okay? And an example of that, an example of a combinatorial optimization problem is the max cut problem. So we say that given some undirected graph with arbitrary non-negative weights, find a partition of the graph's nodes, or in other words, a cut of the graph that maximizes the weights along with the cut. Okay, so the cut weights being like the sum weights Wij, where I and J are basically the nodes that this edge W connects them to. Okay. Visually, you can sort of like imagine this very simple 5-node graph where these are the following edges. You know, some edges are missing. So, for example, we don't have an edge between 1 and 4 or 0 and 3, for example. But the edges that do exist all have weights equal to 1. Okay. So the max cut solution for something like this is very simple. It's basically the cut that traverses these particular edges. And in the form of we can express this solution in terms of a bit string, right? So we can say, we can say like, okay, like, is this node in, a cut is basically a partition. And a partition basically means you sort of divided your graph into, the nodes of your graph into 2 sets, right? And so you can denote whether a particular node is in set A or not, or set S or not, by 0 or a. Okay, so you can say like, okay, 0, 3, sorry, 0, 2, and 3 all belong in the same group. 1 and 4 belong in the same group, right? So like you can say that like 1 and 4, like 1 and 4 bit characters have to both be 1, or they have to both be 0. So these are both sort of like equivalent forms of expressing max cut solution in terms of bit strings. Okay. Now, in a quantum computer, what would be great is if we gave the max cut Hamiltonian, fed it into some algorithm, and the algorithm outputted, precisely an equal superposition over both of those bit strings as the solution. Okay, because like if we were to sample from this state, we would essentially be sampling the solution. Like it doesn't matter whether you call it 0, 1, 1, 0, 1, 0, 0, 1, or 1, 0, 1, 1, 0. They both specify the same particular max cut solution. Okay. So the max cut objective function we saw earlier, it's basically just the sum of the weights connecting the edges between those 2 partition sets. On a quantum computer, we have to express this in terms of qubit operators. So we can re-express this in terms of the identity and the Z operator. So we already saw what the Z matrix looks like. We can express the same thing in terms of the Z operators as follows. And the advantage now is that this is something that can actually operate on qubits. Okay. So the QAOA algorithm then goes in the following way. So we first prepare an equal superposition state as an initial state. So in other words, we'll apply a series of atomars in all our qubits. We define a mixer operator. It seems to switch back and forth quite a bit. We'll define the mixer operator, and it's basically the sum of all X gates on all qubits. And now that itself is not a unitary operator. In order to turn that into a unitary operator, you have to exponentiate it. So exponentiation just basically means like you take the matrix exponential or the operator exponential of that particular operator, and it has some coefficient beta. So this is why this is the variational part of this variational algorithm, is that there's some like parameter beta over here that's so far left unspecified. We also have a cost operator, and so this cost operator is the same as the objective function of the problem. We already saw how this is written in terms of the qubit operators, and this too you again exponentiate with some parameter gamma. And so now the QAOA prescription basically says like you apply each of those 2 operators in sequence. So you apply first the cost operator, followed by the mixer, followed by the cost, followed by the mixer. Each time, having like separate sort of like angles beta and gamma. And now you sample and measure those, and in particular, you measure the expectation value of the cost operator. in this particular resultant state. And same as before, you prepare these particular trial states, you measure the expectation value of the cost operator, and then finally you optimize over these angles, betas and gammas, to find the set of betas and gammas that will maximize the expectation value of the cost operator. And that's going to give you the max bit string. And one thing, this is, so there's a code notebook that's actually going to make you guys work through all of the code in order to implement all of this. And this is actually, as it turns out, fairly simple to implement in Pikewell. But one thing that, sort of like as a preview that you it might help to sort of like acquaint you with right now is so like how to actually exponentiate things in Pikewell is actually very simple. So like, I mean, like for example, this step over here, like you can express these operators fairly simply in Pikewell, but you can also exponentiate those operators fairly simply in Pikewell. So in other words, if you have some angle and you have some polysum, like as you have over here, so like, this is for example a polysum of like several x operators. So you have that part of the polysum. What you do is you can essentially say you loop over each of those terms and you exponentiate them. Basically you take the exponential of this particular term and you multiply that by some angle. And that's going to just like, on adding so like the exponential map to your program. And you'll see all of this in much more gory detail in the code notebooks, but I thought I might basically give you an example code over here as well. And this is just going to result in some like quantum state that looks like that. Okay, so the final thing that I wanted to talk about is noise in quantum computation. So we talked a little bit about how pure quantum states evolve according to unitary operations, and we said about like how unitary operations preserve inner products and therefore the norms. Well, more generally, quantum states are described by this thing called as the density matrix. And the density matrix is the following. So like remember, we now have projection operators for each psi sub I. Okay, so psi sub I is sort of like a pure quantum state, right? And p sub I denotes the probability that you'll find that this general quantum state in that particular pure quantum state. Okay, so you can think of this as sort of like a statistical mixture of several pure quantum states. And this density matrix most generally evolves via cross operations. These so-called cross operations, which are also like specify a quantum channel. So instead of unitary operations, you have these operators multiplying, on either side of sandwiching this row or this density operator. And the only constraint we have on them is that they satisfy this particular constraint. So ki dagger times ki summed over all I has to equal to the identity operation. Okay. And as an example, we can essentially think of like a density matrix that's composed in equal parts of the zeros and the one state. So this, this should not be confused with the plus state. So remember, the plus state was sort of like the quantum dice or the quantum, it was one example of the quantum dice, right? This is not the same as the density operator for the quantum dice. The density operator for something like that looks something like this, whereas the density matrix for a statistical mixture of 0 and 1 looks like something that does not have any off-diagonal elements. Okay? And so here's an example of a quantum channel or a set of cross operators. We're basically saying, pass the quantum state through the channel such that, like with some probability p, it's going to undergo the x operation, and with the remaining probability, it's going to undergo the z operation. And so these define your cross operators, and so essentially what you're saying is that your density matrix rho undergoes this operation or goes through this particular channel. And so this is also something that you'll find in another code notebook that I'll send you guys along, and you'll find that like in find it pretty easy to be able to code your own noise models in Pikewell. And that's essentially all I had to say. Thanks for bearing with me as I went through all these slides. Please do keep in touch. I'm available at Sohaib at Rigetti.com. And you can also join our Slack channel at Rigetti-forest.slack.com. We have a pretty vibrant community, online community of users of Pikewill, as well as like just general quantum computing enthusiasts. So that's it for me. Like, look forward to some coding notebooks that I'll send your way. And thanks for your time.